So we're going to continue our work with volume today. We're going to be talking about the washer method. So far we've been looking at volumes of curves that are rotated, so we end up getting like a solid 3D figure, but that doesn't always happen. So if you needed to look for additional support or videos on this, usually they call that the washer method. This is still 5.2 in our book, so if you want to look in the book, it's still the same section that we're working with. So the first example that we're going to look at is revolving the region enclosed by the graph of y is equal to x squared and y is equal to the square root of x about the x-axis. So I did a little bit of front work here. I graphed the two functions, and we also need to know where these graphs intersect so that when we set up our integral, we know what x values we're using. So to figure out where the intersections are, just set our two functions equal. To solve this, I'll go ahead and square both sides. So x would be equal to x to the fourth. I'll move everything to one side. So 0 is equal to x to the fourth minus x. Factor out an x, so x cubed minus 1. Set those both equal to 0. Our bounds are going to be between the x value of 0 and the x value of 1, which we should be able to confirm graphically, but just to confirm algebraically. So something that's going to end up looking a little bit different with these types of functions is, well, when we revolve this figure here, this little kind of slice around the x-axis, we're going to end up getting a reflected figure that looks something like this. It's almost like a flower petal or something. And when we do the actual revolution, we end up getting a 3D figure, but the inside is actually going to be hollow because kind of we have this like blank space in there. So our work is going to end up being a little bit different. We've been talking about the region really being pi r squared h because that's our cylinder figure, but since we've got this negative space in here, we're going to have to do a little bit of additional work. So we're going to be talking about this in terms of an outer radius and an inner radius to really get rid of that inside stuff that isn't there. So I'll show you guys how to do this. We'll go through some examples, so hopefully when you look at these examples, you kind of get the hang of actually writing the radius as an algebraic expression. But we're going to be talking about this in terms of an outer radius and an inner radius. So our outer radius for this particular function is going to be kind of the bigger radius. We always think about the outer as being the bigger. So my outer radius is going to be my outside function, which in this case is going to be the square root of x, because that's kind of the top function here, minus my axis of revolution, because what ends up happening is my radius actually ends up being this distance from the square root of x down to where I'm rotating, which is just y is equal to 0. So my outer radius just ends up being the square root of x. My inner radius is going to be kind of my lower or my bottom function, which is my x squared. So my inner is x squared minus, I'm going to kind of bring that radius down to my x-axis, the axis of rotation, which is again just y is equal to 0. So my inner radius ends up being just x squared. So the general function or the general equation that we're going to be following for the examples that we're going to be talking about today is going to be the volume is going to be equal to pi times the integral from whatever x value we're starting out to whatever x value we're ending at. And we're still going to be talking about that radius squared times delta x. But since we've got an outer and an inner, now we kind of have to take into account both parts. So it's going to be actually the outer radius squared minus the inner radius squared times delta x. So when I put this all together with my intersections and my outer and my inner radius, my volume is going to end up being pi times the integral from 0 to 1 of my outer radius of the square root of x squared minus the inner radius of x squared times delta x. I'm just going to go ahead and simplify this a little bit. So pi times the integral from 0 to 1, square root of x squared is just x, minus x squared squared is x to the fourth, delta x. And when you plug that into your calculator to evaluate, you should get a volume of approximately 0.9425. So we'll go through one more example rotating about the x-axis, and then I will show you some examples of what happens when we rotate about other lines, kind of like what we talked about yesterday, horizontal lines that are not the x-axis. So go ahead and erase this, erase that top part just so I have a little bit more room to work with. So my second example is going to be working with the function y is equal to x squared plus 1 Y is equal to negative x plus 3, and I still want to rotate this about the x-axis. So I'll go ahead and draw myself a little diagram of what this is going to look like. Oops. All right, so x squared plus 1. So I think that gives me a y, or 5 over here. This will give me a 2 here, y-intercept of 1. I'll reflect that over here. So here's my function, y is equal to x squared plus 1. Not the nicest, but you get the idea. And then my line, y is equal to negative x plus 3. So y-intercept of 3, slope of negative 1. So this ends up being somewhat like this. And then over here, whoa. All right, so the region that we end up rotating is going to be this stuff enclosed in here. And same thing I did with the last one, I do want to figure out where my intersections are. So I'll go ahead and set my two functions equal and solve those out. So x squared plus 1 equal to negative x plus 3. Bring everything to one side. So x squared plus x minus 2 equal to 0. I'll factor that out to get my x values of negative 2 and positive 1, which you should be able to kind of confirm looking at your actual graph. This is my x value of negative 2 over here. This is my x value of positive 1 right here. So my outer radius, since I am revolving this again about the x-axis, is going to be my top function, which is my negative x plus 3, minus, if I bring that all the way down here, my axis of rotation of 0. So negative x plus 3 is my outer radius. My inner radius is going to be my bottom function, which is my x squared plus 1. Again, bring that radius down, minus my axis of rotation of 0, so x squared plus 1. So when I go to set up my integral, my volume is going to be equal to pi times the integral from negative 2 to 1 of my outer of negative x plus 3 squared minus my inner of x squared plus 1 squared times delta x. And you can use whatever online calculator you're using to help you evaluate that. You should get a volume of approximately 73.5133. And just make sure that you are getting these volumes as we're going through these examples, just to confirm that you're doing the correct algebraic steps. All right, so let's move on to something a little bit different. So what happens if we're taking regions and we want to revolve them about lines other than the x-axis? So now we want to talk about the region enclosed by y is equal to x squared, y is equal to x, and we're going to be rotating this about the line y is equal to 2. So I'll draw myself a little diagram here. So here's my x squared curve, and my y is equal to x. Again, not the most accurate here, but I'm doing my best to kind of sketch these quickly. So if I were to draw that a little bit more accurately, we should kind of get a little, again, petal-shaped region in here that we are going to be revolving. But this time, instead of revolving it down to the x-axis, I want to revolve about the line y is equal to 2. So I'm going to go ahead and sketch that line in as well. So what ends up happening here is we actually end up getting something that's going to look a little bit different when we actually do our outer and our inner and kind of our setup here. But I still want to know where my intersections are, so I'll start there. So x squared should be equal to x to figure out where they're intersecting. So bring those over to one side. So x squared minus x equal to 0. I'll factor out an x. That tells me that my intersection should be at x equal to 0 and x equal to 1. Again, you should be able to confirm that up here. But when we go to set up our outer and our inner radius here, my outer radius is going to be my top function minus kind of my bottom function. I know that we were talking about that in terms of the axis of rotation in the last problem, but this one's a little bit different because this time my top function is actually my axis of rotation. So my outer function is going to start up here. So my outer function is going to start at 2 because that's my top. And my outer radius, I was saying kind of before that my outer radius is always going to be like the larger radius. So to make the larger radius, I'm going to extend my top function down to my bottom function because that's going to get me the larger radius. So my bottom function here is the function x squared. So my outer function is going to be 2 minus x squared. My inner radius is going to be, again, starting from the top here. So my top is still 2 minus my inner function, or my kind of taller function, because that's the lesser distance in there. My lesser distance is to my y is equal to x. So my inner radius is going to be 2 minus x. So this is the larger radius, and this is the smaller radius. Outer's always larger, inner's always smaller. So when I set up my integral, the volume is going to be pi times the integral from 0 to 1 of my outer radius of 2 minus x squared minus 2 minus x squared dx. And when you plug that into your calculator to evaluate, you should get a volume of approximately 1.6755. And hopefully when I do the next example, you'll kind of get the hang of like where you're starting to get your outer and your inner radiuses, and kind of how that depends on where your axis of rotation actually ends up happening in your diagram. So we'll go through a couple more examples. My next one is going to be a cubic. So we're going to rotate the region enclosed by y is equal to x cubed, y is equal to x, and we're going to revolve that about the line y is equal to -2. I'm also going to put the stipulation in here too for this one, just so that we're clear on where we're actually revolving. This is going to be any x value that's greater than or equal to 0, just for the purpose of this problem. So I'm going to go ahead and sketch this region. So y is equal to x. Here's my y is equal to x line, something like this. See if I can get a little bit more accurate drawing here. And y is equal to x cubed. So 0 cubed is 0, 1 cubed is 1, 2 cubed would be 8. So this would be somewhere up here. So my region is going to end up looking somewhat similar to the last one. So this is what I want to end up rotating. But this time, my axis of rotation isn't going to be above. It's actually going to be below that region. So y is equal to -2. If I go to sketch in that line, is going to look something like this. So my intersections, again, I'm going to go ahead and calculate those algebraically. You should be able to kind of eyeball them on your diagram, but just to kind of bring that point home, x cubed minus x, I'll bring that over to the other side. So x cubed minus x is equal to 0. Factor out an x. So you end up getting x times x squared minus 1 is equal to 0. You would actually end up getting 3 intersection points here if you were to solve that out algebraically, 0, -1, and +1. But since we are restricting the region to be anything greater than or equal to 0, I will get rid of that kind of middle intersection point of -1. I just want to work from 0 to +1. So let's talk about the outer radius here. So my top function. This time my top function is the line y is equal to x. And I'm going to subtract out, and I'm going to go all the way down to my axis of rotation here. And that axis of rotation happens at -2. So my outer radius ends up being x minus -2, which we can simplify to just be x plus 2. My inner radius is going to be from kind of my bottom function here. My bottom function is that x cubed minus, and I'm going to go down to the axis of rotation here, so -2. So my inner radius ends up being x cubed plus 2. So when I go to set up my volume is going to be equal to pi times the integral from 0 to 1 of my outer of x plus 2 quantity squared minus my inner of x cubed plus 2 quantity squared dx. And when you go through and evaluate that using your calculator, you should get a volume of approximately 3.7399. All right, so one more that is a little bit different, and then I'll have you guys try some on your own. So this one is going to end up being a rational function. So this one we want to enclose by the function y is equal to 1 over x. We're given the stipulation that y is equal to 0, x is equal to 1, and x is equal to 3. And we are going to be revolving that about the line y is equal to -1. So I'm going to draw myself a picture again here to see what this region is going to look like. So y is equal to 1 over x. I'm enclosed by y is equal to 0. And this time I don't have to worry about intersection points because I'm actually given the stipulation that I want to revolve between the x values of 1 and 3. So I'll start at the x value of 1. If I plug in 1 over 1, that gives me a 1. Plug in 2, 1 over 2, that's going to give me 1/2. Plug in 3, 1 over 3 should give me 1/3. So this is going to be kind of my piece here. I'm enclosed by y is equal to 0. Y is equal to 0 is just this horizontal line here. And then I'm enclosing between x is equal to 1 and x is equal to 3. So this is going to be the region that we are going to be revolving. And we are revolving that about the line y is equal to -1. So I'll go ahead and sketch that in. And then I'll draw myself the kind of reflected piece here. I know I didn't do that in the last one, but we'll see kind of why this is changing a little bit in this one. So something like this. So a revolved figure would look something like that. All right. So again, we don't have to worry about intersections. We already know where we're starting from and ending at. So when we go to calculate our outer radius, our topmost function here is the 1 over x. And I'm subtracting down to my axis of rotation, which is -1. So 1 over x minus -1 is going to give me an outer radius of 1 over x plus 1. My inner radius is going to be from my bottom function, which is just y is equal to 0, minus, I'm going to go down to my axis of rotation here, -1. So that's going to give me 0 plus 1, which actually just gives me a 1. Seems weird, but again, my bottom function here is just y is equal to 0, so that's why that's happening over here. So when I set up my volume is going to be equal to pi times the integral from 1 to 3. Again, that was given to me up there, of my outer radius of 1 over x plus 1 squared minus my inner radius of 1 squared dx. I probably wouldn't simplify this at all. I would literally just use your technology to get the volume. You can rewrite that as x to the -1 if you want to. You don't have to if you're just plugging into your calculator. So you should get a volume of approximately 8.9972 when you evaluate that using your technology. All right, so it's your turn to practice some problems. Please let me know if you have any questions.